All right, we're going to look at extrema, or like the absolute max and min of a function. So, um, you're an absolute or a global maximum on an interval if it's greater than all the other values on the interval, right? And then it's an absolute or global minimum on the interval if it's the lowest value in the interval, right? So we have two different kinds of extrema besides max and min, but we have relative or local, and then we have absolute. So the relative or local, I'm just going to draw like a squiggly line here, right? I'm going to do something like this. So this point right here would be a relative or a local maximum because in relation to the ones around it, right, it is a maximum. And for the same reason here, this could be a local or relative minimum because in relation to the ones around it, it is a minimum. And then I'm going to draw a different one to do like an absolute. So usually, well, it depends on the domain of the function. The one I drew was going off to the infinities in both directions, so there was not an absolute max or minimum there. But let me draw something like maybe like this. So I could find some relative max and mins here. And then the absolute is going to be the highest on the entire domain if I'm talking just from this left point to this right point. So the absolute maximum is going to be this one because it's the highest value there. And then this one would be the lowest. So the absolute would be global minimum. Okay? So that's just some examples here. Let's look at this graph here. And we're going to determine the extrema on the interval. So we're going to look for, here, this is what I'm going to do. I'm going to put relative maximums, relative minimums, and then I'll put absolute max and absolute minimum. So sometimes it's easy to look at the entire domain and look for the absolutes first because it's either the highest or the lowest on the entire thing. So right here, I would say that that is an absolute maximum, so at point E. And then an absolute minimum, we want the lowest, which is going to be here at D. We look at the endpoints as well when we're looking at the absolute max and min. But when we're looking at relative, we don't include them because we're not sure what's happening on either side. So I can't say relative to the others around it, it's a maximum or minimum because I don't know what's happening on the other side. All right, now I'll do the relatives. So we have a minimum here at B, a maximum here at C, another minimum here at D, and yes, even though it's the absolute minimum, it's also a local or relative minimum. Same reasoning for E, it being a relative maximum. There we have it. All right. Let's look at this graph. So state the relative extrema of the function. So the relative are the local ones. So let's do max and min. Let's do the maximums first. So I think this one's the only one. I'm just going to give the ordered pair 2, 2. I don't know if I have it anywhere on here, so I'm going to put a star. I might have it somewhere else, but just in case I don't. There's some key words. So if it says what is the extrema, we are looking at y values. But if it says when, then we're looking for x values. We're mainly interested in like the outcomes of things versus the inputs. But I always put the ordered pair if it's not something super clear to me. All right, and then the relative minimums, we've got these two. So -3, -8, and 4, 0. Considering the domain, who are the absolute extrema? So because the domain goes off to infinity, or off to positive infinity, I should say, we will not have an absolute max. But I do think we have an absolute minimum. So if I look on the graph, there is a lowest point. So at -3, -8. All right. Let's get another one here. Find the relative extrema. So let's look for the maximums and minimums. So minimum, we'll just give the ordered pair, 2, -2. And another minimum here at 10, 2. And I wrote that in the maximum spot. That's crazy. I'll just switch it. Min, max. Now some maximums. We got here 7, 7. And that's going to be all for the relative ones. So considering the domain, what is the absolute? Okay, so the highest looks like it's right here. So let's make sure I put it in the right category. So the maximum is 7, 7. And then the minimum, so it's right here at 2, -2. Okay. So we have something called the extreme value theorem, which is cool in a way if we know a function's continuous. So if a function's continuous on a closed interval a to b, then the function has both a maximum value and a minimum value. Because if it's continuous everywhere, then there's going to be a highest point and a lowest point. And then this is also where we check the endpoints as well. And here's just some pictures of where maybe the theorem doesn't apply, and we can look at kind of like why. So for each graph below, explicitly state where the hypothesis fails on the interval 0 to 3, and then determine if we have an extrema. So I know this isn't a proofs class, but the hypothesis is the if part. Okay, so if f is continuous on the interval. So if we are told that it fails the hypothesis, we're just finding where, right? So, all right, 0 to 3, where are we not continuous? Where you're not continuous at x equals 1. But we still might have some absolute max and mins. So let's see, absolute max and min. All this means is that the theorem doesn't guarantee max and mins because of the discontinuity. But we can still have them, right? Because this is the absolute maximum. I'll just write the y value. So absolute max of 4 and an absolute minimum of, we'll call that 1/2. Right? Part B also has a discontinuity, which we know because it gave us in the problem. We just want to know where. We have a jump here at probably looks like 1.5, right? But we do have a highest value right here. So we have a maximum of, looks like 4.5. We'll do our best guess. Then I wouldn't say we have an absolute minimum because I would say it's here, but I have a hole in the graph there. So I wouldn't say that we have an absolute minimum. Okay. All right, we're not continuous on the closed interval. So at x equals 0, because we have a hole there, right? And then we don't have an absolute max or a min because this would be the absolute max, but we have a hole there. And then we don't have a minimum because that's going off to negative infinity. All right, and then the same reason as C, it has to be continuous on the closed interval. So at the endpoint, so x equals 0 and x equals 3, continuous in between, but not at the endpoints. All right. But I do have an absolute max of 4, so max of 4, and then a minimum, which looks like, doesn't look quite at -1, but for lack of wanting to guess exactly what that is, let's just say it's -1. All right, so it's not exactly, but let's call it good enough. Okay, we have these things called critical numbers or critical values, right? So a critical number or value of a function is an x value that is in the domain of the function such that the derivative is either 0 or it doesn't exist. So if x equals c is a critical value, then we have a point, right? We could evaluate the function at that point and get an actual ordered pair. That's called a critical point, okay? We might need that here soon. So find the absolute extrema of the function on the given interval, provided that the EVT is applicable. If not, justify why. So that hypothesis, remember, is if it's continuous, then we're guaranteed to have those extreme values. This is a polynomial function right here, and all polynomial functions are continuous everywhere. It doesn't matter what the domain is. So we are good to go with the EVT here, and so we want to find the extrema, right? So we need to find the derivative first to be able to set it equal to 0 or find where it doesn't exist. So this is going to be what? 24x squared minus 6x minus 9. And then I want to set that equal to 0. There's nowhere on this derivative where we will be undefined, so we are good there. Let's find maybe a GCF. Can I pull out a 3 maybe? So 8x squared minus 2x minus 3. And then I want to find the zeros. So I could do quadratic formula. I'm going to do slide and divide and see if that works. So I slide this number over and multiply. And really, I guess I could divide both sides by 3. I don't need that GCF out there. So now I'll have x squared minus 2x minus 24. And then I think I can find two numbers that multiply to 24 and add to 2. Probably 6 and 4, and we want negative 6, positive 4. So then I have two critical values at, critical values at 6 and negative 4. And we are, let me just do a preview. Okay, this is the last page. We can find if they are max and minimums based off a sign chart. I think we've done sign charts before. If not, they're coming up. But we can go negative 4 and 6. We can say, all right, let's substitute in some values. So if I plug in 0, because that's in between there, that's going to be, let's see, x equals 0. Negative 6 times 4, which is negative 24. And then those multiplicities are odd, so it's going to cross at each of these zeros, so plus and plus. And then we have some sign changes here. And when we have a sign change, we do have a maximum or a minimum. So changing from increasing to decreasing, we have a maximum at negative 4. And we're changing from decreasing to increasing, we have a minimum. And we can plug in and get what those actual points are. So we have a maximum at negative 4 and a minimum at 6. And we can plug that in. And oh my goodness, let me back up because I was doing it on the entire interval. And neither of these values are within that interval. That is crazy. So I'm going to back up a second. That is just some extra information there. My goodness. So we're continuous on this whole interval. So what we would do is we would find the critical points or values and make a chart, and we would test both the endpoints. Oh my goodness. Okay, I realized what happened, and I am gonna just take some steps back. We're gonna go back here. I forgot something. My slide and divide, I slid, but I didn't divide. And that is very important. So So I slid the 8 over and multiplied, but I forgot to divide back out. So that would make sense why it's not in the interval. Goodness. So if I divide both of these, right, let's reduce. So if I reduce both of my 2, what is that, 3/4? And that's 1/2. And that makes more sense. 3/4 and -1/2 would be within that interval. But then either way, I do need to go here and find these values. So I check the endpoints still, so -1 and 2. And then I can plug in these values here, so -1/2 and 3/4. And then I'll just plug this into a calculator to get the function values. All right, so if I plug in -1 into the calculator, I get 0. If I plug in -1/2, I get 4.75. Plug in 3/4, I get -3.0625. And if I plug in 2, I get 36. All right. And then I need to find which one's the absolute highest and what's the absolute lowest out of these values, right? So the highest is going to be 36, and then the lowest is going to be that -3.0625. So absolute max, absolute min. Usually we want the y values, but since I have the ordered pair listed, might as well keep the ordered pair here. All right, let's try again for another one, and let's see if I can do that correctly the first time. So I need to find if we are continuous, to know if we are guaranteed to have a max and min. We have another polynomial, so we are good to go. So let's find the derivative. 4x cubed minus 9x squared. And then I want to set that equal to 0. And maybe I want to pull out a GCF. How about x squared? And I'm left with 4x minus 9. So then I have two values. I got 0. And then, what is that, 9/4? Right? And then I am going to now plug that in to our little chart. I want to test the endpoints as well. So -2 and 2. And then any that are in the interval. So 0 and 9/4. Right. Now I'm also going to plug this into a calculator as well. Do that pretty quickly here. So our function is x to the 4th minus 3x cubed minus 1. And now I just want to evaluate it at these different values. So -2 gives me 39. 0 gives me -1. 9/4 gives me -9.54. Decimal keeps going, but that's all I'm going to put there. And then 2 is -9. All right, so the highest value is 39, and the lowest is -9.4. So there's my absolute max and my absolute min. Let's try with another function here. So we have x e to the 3x. So, should be continuous everywhere. Where I think about where things are not continuous is if we have a fraction in the function, because we can't have a denominator that's equal to 0. Or if we have log functions, because we cannot take a log of a negative number. And I think for here, we are good to go. So let's do a derivative. So I have to do product rule here. So left d right plus right d left, and let's clean that up. So that's 3x e to the 3x plus e to the 3x. Let's go ahead and just take a GCF out, right? Let's take a GCF of e to the 3x out. So then I'm left with 3x plus 1. So I get negative 1/3. If I set this all equal to 0. And then the exponential function here, e to the 3x equals 0. If I want to get the exponent now, I can do natural log of both sides, right? Well, natural log of 0. There is an issue. We are undefined there. So the e to the 3x will never be 0. So I only need that negative 1/3. So I can go, all right, x and then g of x. We want to test the endpoints as well as that critical number. So let me plug this in a calculator again. So we have our function is x e to the 3x. And we want to evaluate at negative 1. Oh, I didn't leave myself enough space here. That's negative 0.0497. Negative 1/3 is negative 0.1226, and it keeps going. And then if I plug in 0, I should get 0. So we actually have a maximum of 0 and a minimum of whatever decimal that is. So minimum, maximum. All right. We have a log function here. So we have some issues. We need that middle chunk, what we're taking the natural log of. We need that to be greater than 0, right? So let's see, I can add 9. X squared has to be greater than 9. So that means, and we got to think negatives as well. So x would have to be greater than 3, right? And then if we think on the negative side, x would have to be less than or equal to negative 3. So we have an undefined section from negative 3 to 3, which means we're not continuous on this entire interval, right? Negative 2 to 5. So we're not guaranteed to have a extreme value here. So we're going to leave it as it is. All right, let's check this function. So we don't want a 0 in the denominator. So x squared plus 4 equals 0. X squared is negative 4. So we're continuous for all real numbers. Okay, so we're good. Let's do a derivative. So quotient rule here, low, d high minus high, d low, all over low, low. Let's clean it up a little bit. So it's going to be 3x squared plus 12 minus 6x squared, all over x squared plus 4 squared. Combine some like terms, so negative 3x squared plus 12, all over x squared plus 4 squared. And now we want to set this equal to 0 and find where it's undefined. Well, we already know that x squared plus 4 is defined on the real numbers. So that denominator, setting that equal to 0, we're not going to get any real numbers that are going to work. So we are all good for that denominator. I just need the numerator set equal to 0. I can take a GCF of negative 3 out, right? Be left with x squared minus 4. So then, okay, this will give us plus and minus 2. But we are only looking at the interval of 0 to 4. So in my little chart to find my values, I'm only going from 0 to 4. So that means I wouldn't take the negative 2, but I can take the positive 2. And then I can plug this function into the calculator again and find those values. So my function is 3x over x squared plus 4. And I want to evaluate it at 0, which is just 0, and then at 2, which is 0.75, and then at 4, which is 0.6. So maximum and minimum, right? And then that is all for the absolute max and minimum section. So if you have any questions, let me know.